Okay, so in this video, we're going to talk about hypothesis testing with ordinary least squares regression. Keep in mind that we're starting with a bivariate framework where the independent variable x is continuous and the dependent variable y is also continuous. So since it's a linear relationship, the only possibilities for us is that the relationship between x and y is positive as x increases, y increases in a straight line, or as x increases, y decreases, which would be a negative relationship, also in a straight line. So the null hypothesis in a linear relationship would simply be that in words there's no relationship between x and y, or if we're talking about the slope of the line, that the slope of the line is neither positive nor negative, that is, the slope of the line is flat, or the slope of the line is 0. So as you can see how we've written here, h subscript 0 is the statement that beta, the slope coefficient, is equal to 0, so that as there is a 1 unit change in x, there is a 0 unit change in y. The alternative hypothesis is that there is a relationship between x and y. So in this case, we're saying that the slope is not 0, which means that the slope can be either positive, that is, beta is greater than 0, or the slope can be negative, which is the statement that beta is less than 0. So the way we test the null and alternative hypotheses are very similar to the ways we thought about testing difference of means or even chi-squared. And that is, we're going to look at the variance, and we're going to see how much the variance is spread around those estimates that we're getting, or around kind of our expectations that we're looking at in our model. So recall from our previous discussion that we start with a scatter plot, at least in the bivariate case, and what the regression analysis is doing is it's fitting the best fit line to those data points. And when we say fitting the best fit line, it is picking the best line out of an infinite number of lines and returning the slope coefficient and y-intercept for that line. So in terms of hypothesis testing, we're actually not just going to test the slope coefficient to see if that's different from 0. We can also going to have a test for the y-intercept to see if the y-intercept is significantly different from 0. So I'll kind of take our previous example where we had our graph where we plotted midterm grades and final exam grades, and we kind of see a positive relationship. That line is y equals 0.98 times midterm grades plus 1.05 as the y-intercept to give us the final exam grades. And we kind of see then that line overlaid on top of our scatter plot. You'll also notice here that the r-squared value is given us to the top right corner of the graph, and the r-squared value is 0.584, so the r-squared is telling us that the midterm grades are a fairly good fit of the final exam grades. Kind of a loose interpretation is that 54% of the variation in final exam grades are explained by midterm grades. So let's illustrate, though, how variance in our data leads to different confidence levels for our slope and y-intercept. So here what I've done is I've deleted all of the actual data points in our graph, but I've kept the same slope of y equals 0.98x plus 105. Here I've overlaid 8 red dots, and you can see here that the 8 red dots are really close to the line that we've estimated. So what we would kind of say here is that we have, probably based on these data, high confidence in the line. That is to say, you couldn't really see yourself drawing that many different lines from the one we already have to characterize these data. So we would be pretty confident that this is a pretty accurate slope for these data points and a pretty accurate y-intercept for these data points. In this case, we might imagine that r-squared would be very high because we're explaining a lot of the variation in our data. So we might guesstimate that our I-squared value would be something like 0.9. But let's further suppose that we added some more cases that added more variance to our data. So here I've added a series of blue points. I've added an additional 6 cases that are spread out more along that line. Here we would have less confidence in our slope and y-intercept because we could imagine that we could draw different lines to our graph that could also characterize these data points. So here, by increasing the variance, we're decreasing the confidence in our slope and y-intercept, and we're also decreasing the amount of variance that our model or our line is explaining. So here our r-squared value might drop down to, let's say, 0.7. So here for just one final illustration, I've added a series of additional points, a third set of points. This time they're shown in green. And you can see that the green points add even more variation around that line. So we would lose our confidence compared to just when we have the blue points or the red points of the line by adding the green points, because we can imagine even more slopes and y-intercepts that could characterize these data points just as well as our slope of 0.98 and our y-intercept of 1.05. So really, once again, the major takeaway here is that the more variation you have in your data around your slope and y-intercept, the less confidence you're going to have that slope and y-intercept are a good characterization of the relationship in your data. So getting back to the primary question, we're really asking how confident are we in the estimated slope and estimated y-intercept. In particular, we want to know how confident we are that the estimated slope is not equal to 0, which is what our null hypothesis says. And actually, there's the second hypothesis, which is for our y-intercept. And we're also asking how confident we are that the y-intercept is not equal to 0 in our analyses. So fortunately, it turns out that the statistical test we're going to use for both the slope and y-intercept is something we've already seen, and that is they're going to be t-scores. The logic is very similar, where t is going to be equal to our observed value, in this case for our relational hypothesis. We're going to look at the slope of beta. We want to know, does that beta statistically differ from 0? So we're going to say beta minus 0 in the numerator divided by the standard error of beta in the denominator. For the y-intercept, it's the same thing. T is going to be equal to our estimate or observed value of alpha minus 0 divided by its standard error. Now, unlike when we looked at t-scores and chi-squared, we're not going to spend a lot of time talking about how to calculate these values. So for our purposes, we're going to really just rely on the beta estimate, the alpha estimate, and the standard errors for both beta and alpha that come from our analyses in our statistical program, in our case SPSS. So here I've just copied over the slope-intercept from our regression analysis of 0.984. And I've also copied over the standard error that SPSS outputted, which is 0.196. So to get the t-score for the slope, we would take our 0.984, subtract 0, and divide by 0.196, which gives us a t-score of 5.025. Now, if you remember from our previous discussions, if you look at the t-table, generally you need to get a t-score of about 2 to be significant at the 95% confidence level. So here you can see that we are exceeding that 2.0-ish threshold for the 95% confidence level for a t-score. So we would have enough evidence here to conclude that there probably is a relationship, and therefore reject the null hypothesis that midterm grades and final exam grades are not related, or that the slope of midterm grades and final exam grades is 0. Looking at the y-intercept, here we're taking once again the estimate for alpha, subtracting 0 and dividing by its standard error. So copying those values over from SPSS, we have a y-intercept of 1.049 minus 0, divided by a pretty big standard error of 17.38, which gives us a t-score of 0.060. Once again, using that rough guesstimate of a 2.0 threshold for 95% confidence, we can see that we are far below that confidence level, and here we would therefore conclude that we do not have enough evidence to reject the null hypothesis. So we would fail to reject the null hypothesis, include that the y-intercept is not statistically different from 0. And the final point here is that if you do want to use the table and the critical value method of checking for statistical significance, you need to be able to calculate degrees of freedom to use the rows in the table. So degrees of freedom for a regression parameter is n minus p minus 1. N is the number of cases you have in your sample. P is the number of parameters you're estimating. So in this case, it would be 2 because we're estimating the parameter for alpha and the parameter for beta minus 1. So we would have, in our case, 20 minus 2, which gives us 18 minus 1 for 17 degrees of freedom in this analysis. Once again, you really wouldn't need to do this if you're using SPSS, because SPSS will give you the significance level or the probability the null hypothesis is true automatically, which we'll talk about and look at more carefully in the final video in this set.